Okay, acid and base properties of salt solutions. So the first thing that you'll be asked is to determine the parent acid and parent base of a salt. This is a salt. It's an ionic compound, so it's a salt. And what you do is you break it up. The first part, the cation, generally a metal, is going to be coming from the base. And what we do is we add to it OH minus. And then the counter ion, the anion, came from the acid, and we add H plus. Well, when you have lithium ion plus OH minus, that goes to lithium hydroxide. Bromine plus H plus gives HBr. Now I said, well, why did they call these the parent acids? Oh, good question. If you put these into solution together, they will form 100% lithium bromide and then water. Usually water, but an acid and a base form a salt, and usually water, or often water. So that's where they come from. Now the thing is, that's nice, but if you see a salt and it is, this is a strong base, and this is a strong acid. If its parents are both strong, then lithium bromide solution is neutral as far as the pH. So it has a pH of 7. So any salt that has a strong acid and strong base as parents will be, when you put that salt into solution, it will be neutral. Now here we have a NH4. Now this is an unusual one. We put OH minus, or attach it, and we get ammonia. And ammonia is a weak base. Cl plus H plus gives us, so this is the procedure you use each time. This one's a little tricky, but once you see it once, now you know. Ammonium ion, and it's very common because we need salts that have a weak base as a parent, and I almost always use ammonia for the weak base. There are other ones, but they're not like acids. The weak bases have very different structures from one another. So you can look in the list of weak bases that we have, and you'll see. So I like to just use ammonia. And then we have a strong acid. Well, if you have a parent that is a weak base and a strong acid, that means that this salt solution is acidic. The strong parent wins out, we can say. And in the next problem I'll show you why. But for now, that's a nice little thing to keep track of. So the pH is going to be less than 7. So if you have a strong base and strong acid, if both parents are strong, they cancel each other, and it's neutral. If you have a weak base and a strong acid, you have the strong parent wins out, so it's acidic. And you might guess that we're going to go through every combination here. So Na plus OH minus, its parent base is sodium hydroxide. If you react it with, well, let's get it first here. If you reacted sodium hydroxide and HCN together, you get sodium cyanide. Now this is a strong base, this is a weak acid, so which one wins out? The strong one does. So sodium cyanide solution is basic, and also very, very deadly. So pH greater than 7. Now, for this one we have, and you don't have to write this out. If I ask for the parents and you can just look at it and see, that's fine. Unless I'm really specific about it. I might ask you to show it, but that doesn't sound like me. So we have a weak base and a weak acid. Now we have a problem because neither one is dissociating completely. This one is we need to determine the acidity, well, we'll say the pH. And that's what we'll do in the next one. So this one is, what's the pH? It's unknown. We can figure it out, but it's not as easy as these other ones. So you have that going for you. Make sure we have everything on here. Okay. Now, there's two ways to do these problems that I'm about to do here. Determine if each of the following solutions is acidic or basic or neutral. For this one, I just say neutral. Done. But let's show why. So the sodium chloride, when it goes into solution, it breaks up into sodium ion and chloride ion. And so the sodium ion will react with water. We had it reacting with OH minus. That was just to find the parent ions. But when sodium ion goes into solution, into water, or it's dissolved in water, it is going to react with the water. And this is a process called hydrolysis. Well, water only has H plus or OH minus to give. Well, the H plus is not going to go with the sodium ion because they're the same charge. So it must be the OH minus. So we'd get sodium, and we'd leave sodium hydroxide, and we'd leave behind H plus. The chloride ion would hydrolyze with the water. It would hydrolyze to HCl and OH minus. The problem is that these are both strong. This is a strong base, and this is a strong acid, like we mentioned before in the previous problem. So since this is a strong base and this is a strong acid, they're going to dissociate 100%. So in other words, for each of these, it's no reaction. Since there's no reaction, that means that there was no H plus or OH minus that was produced. So this would be neutral. So it goes into neutral water. Sodium ion and chloride ion do not react with water, so there's no production of either OH minus or H plus or H3O plus. So it's neutral. Okay, so that was an easy one. Here we have the parent is a strong base and a weak acid, so this should be basic. So if that was my only question, you could stop there. You could say you want to explain that this salt came from a strong base and a weak acid, but let's see what happens here. The K plus goes to water. The only thing it can produce is KOH and H plus. So since that's a strong base, which would instantly break apart, so it's not going to form. Even if it formed for a nanosecond, it would fall apart. So this is no reaction. Oops. And then we have NO2 minus reacts with the water. It produces HNO2. Now we got something different. This is a weak acid. It likes to be in this form. So it is an equilibrium, but it likes to be in this form, and it is going to produce some OH minus. No H plus will be produced by the counter ion, OH minus, so that now we've tipped the balance, where we no longer are neutral. We have some OH minus, even if it's just a little bit. So this is basic. We have more, so the pH is going to be greater than 7, just like we predicted. But now you see why it works. Okay, now we have this guy, and NH4 plus water is going to produce ammonia and H3O plus. Br minus reacts with water, and it's going to produce HBr. You can stop there because you can see it's a strong acid, but let me just finish it up. So this is a strong acid. It's going to react back and go right back to the start. And then we have, this is going to produce H3O plus. And this is a weak base. And it likes to be in this form, so this H3O plus is going to grow and in concentration. So this is no reaction below, so this is acidic. And so pH less than 7. And we could have predicted that here. We'd see this is a weak base, strong acid, so it should be acidic. Okay, now the last one is a little tricky. And I don't know if I have... Yeah, last one has its own page because it's going to take a little work. Now this is, we can see this comes from a weak acid weak base. Weak acid, and this is the weak base. So when it goes into solution, the ammonium ion is going to do just like it did in the previous problems, but I'm going to rewrite it. And then we have H3O plus. And I don't know if I've been putting the phases in. I should. If I don't, I think you can tell that these are in water, but and OH minus. So we can see that this conjugate acid of the weak base is going to produce H3O plus, and then the conjugate base of the weak acid is going to produce OH minus when it goes back. They're trying to get back to their stable forms. So we have their conjugates and they try to get back to the stable forms. They like this side, so one produces H3O plus, one produces OH minus. Neither go away, neither is a no reaction. So now we have to determine which one produces more. Well, this is an acid, so it has a Ka, and this is a base, so it has a Kb. In the table though, we get all we're going to find is the Kb for this and the Ka for this one. So what we have to do is use that expression, and this is for an acid and its conjugate base, or its base and its conjugate acid. So we need to know the Ka for NH4, because that's what dictates how much, that's telling us how much H3O plus is going to be produced. And we need the Kb for this to tell how much OH minus is produced. So if the Ka is greater than Kb, so, and that's the Ka for NH4 plus is greater than the Kb for C2H3O2 minus, then it will be acidic. If Ka is less than Kb for these species, then it will be basic. And if by their slight chance that they're the same, then it'll be neutral. So we have to determine, using this expression, we have to determine the Ka for ammonium ion from the Kb of ammonia, and the Kb for acetate ion from the Ka of the acetic acid. So we have a little work to do here. I was hoping that I could. Do I have it here? Here it is. Okay, good. Alright, so we have Kb for ammonia is 1.8 times 10 to the minus 5. Ka for for acetic acid is 1.7. They're very close. Probably shouldn't have used that, but it still works out. One is gonna be different from the other. So the Ka for ammonium ion, we figure that out. That is going to be equal to Ka is Kw over Kb, or 1 times 10 to the minus 14 over Kb, which is, just going to put in the right significant figures. And this comes up to be 5.56 times 10 to the minus 10. Kb, so now we know our one number. Kb for acetate ion, well, that's found. Kw, same way. We just use the Ka for the acetic acid. And there's really no way of making a mistake about which Ka and Kb you should use, because you'll have the table, and if you try to find the Kb for acetate, you'll have to go to the Kb table. You won't find it there. And you'll also notice that it's an ion. So you'll have to stop and think about, where is that information? And if you came up during an exam, I'd say, well, you have it. You just have to find it. So you'd go to the other table. Oh, that's right. It's acetic acid, and I have to convert it over. Now we can see that Kb is slightly higher than Ka, and that's all we need. So this means that the solution must be basic.